So, hello. Hi, my name is Jan Bessay. I'm from Dortmund, and I've organized Unsound together with Marco. Today, I want to talk a bit about what do we actually mean by unsound. So this is meant to be a sort of introduction to the concepts and the theoretical foundations of a bit of theory. What is unsoundness in software verification? So let's start right ahead. So in the general picture, we have some system which has input and output, and we want to say that the system implements some contract. This contract may have rules, may establish some properties of the system, but in general, it's okay. Marco's telling me that there's an audio issue. Okay, better now? Okay, great. So back to the general picture. So we have some system that implements some contract with rules and properties. And yeah, that's all we want. So now what could go wrong? One of the things that can happen is that our tool doesn't properly check that the contract is actually implemented. This is indicated by the first picture on the left, where there's this flash going on at the implementation arrow, and we have some bug there, for example. Another thing that could happen, and we will see that later today in the workshop, is that actually the contract and the rules aren't proper. This could happen if they are like unimplementable, for example, but it could also be that the logic or the language to express these rules and these properties of our system is somehow not adequate for what we want to do. So we have a kind of ill-specified contract. And for the purpose of this workshop, we will just say that any tool that either deals with ill-specified contracts and allows us to input them and accept those contracts, or that accepts systems which actually violate the contracts we specify, is unsound. Okay. However, we can have a bit of a more formal definition too. For example, if we look to logic, then a central concept of logic is inconsistency. We say that a logic is inconsistent if in the empty context we can derive false. So what does that mean? Why is that bad? If we have those two other properties of our logic, either like is rules directly supported by it or maybe derivable from some other rule, which are ex falso. That is, if we once can derive false, then we can derive anything. So if we have a contradiction somewhere, we can basically turn that contradiction into a proof of any other formula phi. Then we can basically prove everything. But that might not just be enough, because if you look carefully to the definition of inconsistency at the top, it says that inconsistency must be derivable at the empty context. And so if we want to actually use this for most statements, our logic would have to specify something like weakening, where we can just extend our context and make it a bit bigger to have all of our current assumptions in it. And if we have those two, and we can somehow derive false from the empty context, then our logic becomes trivial or inconsistent, and we can actually, in any context, derive anything. And that, of course, means that the entire concept of contracts, rules, properties of our systems becomes meaningless, because for every contract I can verify, I could as well verify another contract that's saying exactly the opposite, and then that's, of course, nonsense. You might also ask, what about logics where this is not happening? Those could actually lead to some interesting design spots. As far as I know, those design spots aren't really much explored. For example, in some linear or relevant logic systems, you might not have weakening. And so even if there's a contradiction derivable somewhere in the system, it might not leak into other parts of the system because it's not possible to just weaken any context and make it arbitrarily large. Or it might be the case that you can have contradictions in your logic, but there's no rule like the exfalso rule, which allows you to derive anything from contradiction. So you might be happily dealing with those contradictions. It could be the case that those systems make sense in the area of program verification. I personally haven't seen them yet, but it would be very interesting to have someone explore this further. Okay, what else can go wrong? I said earlier that also the implementation side can go wrong, that even if our contract is sort of well specified and there's no logic bugs, then we might have some implementation issues. And here, those are formally captured by the notion of an interpretation. We say that an interpretation goes from some domain A to B, and it's unsound with respect to some property that is either living in A or living in B. If we can find some term or system state or some part of our system such that P of A, so PA of M holds, but once we have translated everything, the property, and that is the property interpreted in the domain B, does no longer hold. And there could be a lot of things like this. I will show one of them in the next slide. For example, wait a second. There we go. For example, it could be the case that equalities are violated. That is, we pick as our P a binary relation, which is an equality relation. And in our domain A, we have M equals N. But then when we interpret things into our language of contracts, for example, then M is no longer equal to N. Or it could be the other way around, that in our language of contracts, two things are equal, M equals N, but in our actual system, those two states or those two programs or whatever we like to describe there are no longer equal. And this can have really, really confusing effects. Like, for example, if we have some function, f here, and we have m equals n in A, and then we, of course, can deduce by the functionality property of f that fm equals in A fn. Otherwise, it wouldn't be a function, it would be a relation. However, now, if we just translate everything to our other domain B, and then we apply just the same translated function to the translated elements, and assuming that our translation even gives us a function, it now so happens that because the translated elements that were previously equal no longer need to be equal under the translation, also the application of the function to them no longer needs to be equal. And so our translated function, even though it's still a function, now in the domain B sort of behaves like a relation, mapping equal elements in the untranslated domain onto non-equal images in the translated domain. And that's, of course, absolutely weird. We have something that is in between functions and relations, and that will confuse the hell out of us if we actually try to use it. There's also something that is even worse that classifies as unsound. There's this version where both logic and semantics have an issue. And this is indicated here by having two of those red flashes. And that is if we actually have what is called an unsound model. And I've taken here the case for logic. You could also do this in type theory or any other like formal system. And what does it mean to have an unsound model? An unsound model is pretty much what we had in the previous slide, just a bit more geared toward the logic of the implementation language or the modeling language. And we say a model is unsound for some logic if there exists an environment gamma and a formula phi such that phi is validated in gamma. However, once we do the interpretation into some other domain or into our model, then the interpreted formula no longer holds in the interpreted environment. And examples for these are pretty abundant, and we will also see some today. One of them that I found in literature is that, for example, reference semantics, which are commonly used in O languages to do aliasing analysis of objects. If we try and use a model for something that was developed for something where we have reference semantics and apply it to something that has semantics such as language like C, which has pointers, and we all of a sudden get overlapping fields, then this is an unsound model. Why is this an unsound model? Well, precisely because we have a contract that would say something like, in our model, it's not the case that memory location X is a null pointer. However, if we have overlapping pointer access to things, which can't even be expressed in our model language, it might be the case that something in our program behaves differently, and that our actual program would say, oh, memory location X is a null pointer. And that, of course, is bad because that might make our program crash. It might cause security bugs and whatever. Today, we will also see other examples, especially by Jamin and Marco. They will be talking about unsound models for object-oriented languages. And these have to do with these mainly have to do, I should say, with the property that the models that we commonly use in OO verification don't properly deal with termination analysis. And so we might have a model that always assumes terminating programs, but the actual programs have a different behavior. And so we again have this unsoundness property that the actual system has something non-terminating encoded somehow in the formula phi, while the model says, oh, that can never happen. Why is it so nice to actually have sound models? Well, this ties also back to consistency. Suppose you have a consistent model, that is one that cannot derive bottom or some equivalent of bottom, and that we have some sound translation. And then we know that our logic that we translate from must also be sound. And that is because it cannot be possible that we have a formula phi that is derivable in our logic, but not derivable in our model. And so if our model could derive anything, that wouldn't give us much, but if it's consistent, it's actually not possible that we derive false from our original logic and then cannot derive false in our model language. And so soundness saves us here. And this is very nice and often used and abused in mathematics. So there's these two guys on the right. The top one is Gödel. The lower one is Doron Zeilberger. And Zeilberger, for example, has a large beef. He's a contemporary mathematician. He has a large beef with Gödel. And mathematicians who just accept Gödel's incompleteness, because well, what do we have in regular math? Very often we have the situation where people just take Peano arithmetic or some version of set theory, Zermelo-Fraenkel set theory usually, as a consistent enough model. So the property at the very top, that's not actually provable, or you would require ever stronger systems to prove it, and then you end up in the situation, as Gödel has shown, where you cannot prove anything about your stronger system anymore without going to an even stronger system, and so on and so forth. And so there's the danger here that if for some reason the consistency of Peano arithmetic or set theory becomes questionable, then all of these soundness proofs of other logics that just relied on having a sound consistent model in Peano arithmetic or stronger, they would also collapse. And right now, as it is, no one would probably be able to track all of the mistakes down unless there's like a very large push in theorem proving. That would be in an enormous amount of work. You'd need 50 years and spend lots of resources on it to find every single place where something is broken if we actually find that one of these things isn't consistent. And so people like Zeilberger, for example, they argue that we should really go beyond Peano arithmetic or set theory and just start fixing them and turn them into versions which are actually slightly weaker, where we actually can prove that we have a consistent model. Such things might happen, for example, by removing the infinite properties of systems. Maybe more relevant for us in software verification is that we often use theorem provers to model our systems. And those, of course, could also be logically inconsistent. And it will require constant vigilance to actually check that those remain consistent, because they could have bugs, for example. And in the last citation here on the slide, there was one bug where it was actually possible to prove false in Coq. We will also see later what measures the Coq community takes to prevent this nowadays. And if that happens, we are no longer sure that what we've actually proven about our systems is actually true, or is at least true with respect to the model of the theorem prover that might just have an issue. However, there's also other things that go even beyond just implementation bugs in theorem provers. It might be the case that by some very subtle thing, like for example, if we take incompatible assumptions into these provers, we might also end up with an unsound system. An example for this would be there's this thing called uniqueness of identity proofs that says whenever I have an identity proof, no matter how I computed it, I can always reduce it to a simple reflexivity assumption, or a simple reflexivity proof, I should say. And so all equally typed all equally typed identity proofs are equal, because I can always reduce them to the simple reflexivity term. And there's another, so that can be very useful, and that's, for example, used in pattern matching in ACTA, or in traditional ACTA at least. And then there's another more modern assumption that we want in our theorem provers, which is called the univalence principle. And the univalence principle basically says, in layman's terms here, that should be enough for our current discussion, it says something like whenever we have equivalent assumptions, we can turn those into equal assumptions. And now, lo and behold, it turns out that if you combine those two in one system, then the entire system becomes unsound. It just doesn't just become unsound, but it's also inconsistent. You can derive anything from such a system. And so theorem provers actually have to take very, very careful steps to make sure that all of their theoretical underpinnings are compatible with each other. And as those things evolve and as they are living artifacts and we find more and more useful things that we want to put into them, this can become growingly hard. And some theorem provers, such as Koch, are even built so that you can add your own axioms into them. You can, for example, easily in Koch say, I can add univalence as an axiom, and I can add uniqueness of identity proofs as an axiom, and Koch will happily accept that and let you do that. However, then you end up in a fragment that is no longer consistent. And so while using those tools, you could make an error as soon as you turn on some axiomatic things. You could actually make an error that makes the entire system inconsistent. And unless you're extremely careful, you wouldn't even know. That's why most people actually, or that is one of the reasons that most people actually refrain from turning on any axioms, because you never know what's going to happen. And even worse, you never know what's going to happen if you have an axiom in your own library of proofs that is then included into another development by someone else. Because they might have another library in there that maybe uses another library that transitively uses some axiom hidden somewhere that clashes with what you have. And systems such as Koch give you a way to analyze which axioms are actually used in your full development. However, if you are developing a library again, then you have to rely on your users to actually do that. And yeah, it's clear that this can lead to trouble. And even if we go beyond just theorem provers that are implemented somewhere, if we just look at their pen and paper underpinnings, it might be the case that someone just missed something. For example, in the original proposal for type theory, like for type theory with dependent types, that is, by Martin Löw, there was some subtle error that caused the type of a type to be a type. And this can lead to paradoxes that are a bit similar to set theory, the set of all sets. Here it's called Girard's paradox because Girard actually found it first and fixed it in Martin Löw's type theory. And if we find something like that, then also it draws into question, what did we actually prove with our theorem provers? And there's theorem provers out there, or dependently typed languages, which are actually happy to accept these paradoxes and just live with the inconsistency. For example, if you look at the release notes of modern versions of Idris, you would find that Idris just blatantly states we have type and type, and you shouldn't take those guarantees that you seem to get from the system for just, or you shouldn't just take them for granted. You should also do software testing. And then, of course, you can argue, do I get any guarantees out of this? Formally, maybe no. Practically, maybe you get some, because, well, yeah, you can prove anything. You'd still have to jump through some hoops to get to the fragment that is actually unsound, and you can easily stay in a fragment that, once they fix that soundness issue, can remain valid. You just never know in which one you are at the moment. And this brings us to the question, if we have an unsound model for something, like we've seen on the earlier slide with the null pointers, isn't that just a bug? Well, I would say that if you have something where it's just some implementation and some contract that isn't checked properly, then maybe that might be fixed. So, for example, if someone made a verification tool and they forgot to put in some if somewhere, and the tool just accepts some corner case that it really shouldn't, then that's a bug and should be fixed. But that's like the unsound interpretation thing that I showed earlier. So that would be one of the left pictures down below. You might also have an inconsistent logic. As I've explained on the last slide, there might be a bug somewhere in Coq that, for example, allows you to prove false, and that might also just be a bug and be fixed. However, when you have actual model unsoundness, so when you're actually using a model to describe your system, and the model just isn't strong enough to predict all of the behavior of the system and to describe all of its properties, and the model just forgets about things. So we have states of the systems or properties that hold in the actual system but are not expressed in the model. And then I would argue that unsoundness in that sense is even more than a bug, because actual behavior is missing. And in these cases, something like Thomas Kuhn, who is depicted here on the right, the philosopher Thomas Kuhn, he argued for the requirement of something like a paradigm shift. So when our current models of explaining things start failing in philosophy, it's usually time for a paradigm shift, as it was when the Newtonian model of gravity failed and we needed to shift our paradigm to go to Einstein. And for some areas, I suspect that in the upcoming years, we will see such a paradigm shift. Maybe this workshop will lead to something like this. That would be like really cool if we could manage this. But we will see arguments that something like this might actually be necessary. Marco will talk about that later. And so when we are at this situation, we are beyond just having a bug. So I've so far just talked about very, very specific, narrow things that have to do with logic and interpretations and bugs in specific things. But I would say that the issue for the Unsound workshop should also be a bit broader than these very narrow technical specifications. For example, if we first stay at the technical specifications for a bit, if we look at type systems, we might have inconsistency in the form that every type becomes inhabited. That's like pretty clearly mapping to the theoretical underpinnings that I was explaining. But there's also another class of errors in our systems that I would consider unsound, that doesn't really match the models that I was describing earlier. And that would be a failure of subject reduction. So if we have some program M that has type A, and then we somehow evaluate that program, for example, by doing some beta reduction, and we get out a program N that is just a simplified version of M, and type A is no longer valid for that simplified program, then that's some bug in our way of specifying contracts. And that's a failure of subject reduction. And this can also have bad consequences. For example, in current versions of Java, subject reduction is broken. So you can get class cast runtime errors in programs that don't even use a cast. And that's obviously bad because your software might just crash. And if your software is important for something, for example, you're having a Java server backend selling very important concert tickets, and hundreds of people are spending sleepless nights to get their ticket, and then nothing works, it will be annoying. But going from this very narrow sense to something broader, there might also be unsoundness issues in the way we model our resources and hardware right now. For example, very few of our formal approaches tackle something like a Stack Overflow. We just assume that we can do infinite or basically infinite computations that are arbitrarily large on our computers without any care in the world. But in practice, our programs would probably crash either because the stack is full or the heap gets full. We also have cost models that don't really capture what's going on. So if you think of big O notation, we usually manipulate arbitrarily large numbers in big O, for example, doing addition in something like a for loop that in big O notation gets arbitrarily large. We just assume that it costs one cycle or one abstract cost unit to do that arbitrarily large addition. And that can't be really the case, because if you actually know how gates and additions work, and if you have ever looked into an arbitrary position number library, you will find that O of one number addition just is impossible. And so we are doing a bit of oversimplification there that has proven to be somehow useful, but it's questionable if it just will remain useful forever. For example, these cost models also don't address any kind of caching. And we now have computer systems on real hardware where the difference between the memory and the cache access is 1,000 or 10,000 fold or even larger. And so it becomes questionable if we shouldn't just have more advanced cost models, even though our students would probably hate it because they already have always trouble to wrap their head around the existing ones. We might actually have to go forward at some point, as painful as it might be to change everything. And then also in that regard, there might be hardware failures. When we build our theorem provers, we always assume, or at least all the provers I know, just assume perfect hardware, where it's impossible that a bit in memory randomly flips, or that something isn't copied correctly from one register to the other. And of course, in reality, that's just not the case. But then there's even like more sort of fluffy things around. For example, there's deployment. We normally, when we develop software and do verification, we have this "it works on my machine" attitude, where actually it's unsound to ignore the operating system environment that our programs might run in. And especially what happens if that environment changes for someone else. I mean, try installing a modern theorem prover on Windows, Mac, and Linux for a day, and you will find that it's always broken on at least one of those platforms. And yeah, how do we even address that? There's, to my knowledge, not much going on in that area. In industry practice, it's also a big deal. You have these large, complicated CI pipelines that are always broken because people have this idea, okay, in order to make the deployment better, I will have a server that actually builds and deploys my software and runs the test in a specified environment. That's, of course, a step forward. But with regard to formal verification, I haven't seen anything remotely addressing something like CI so far. And then even more fluffy than that, and maybe even more to the dislike of someone who lost these Greek letters and symbols and whatever in the formal sense, there's also some social issues that get in the way. For example, we have shortcomings in the way the scientific process works. There's this unsound model of the selfless, omnipotent scientist who will always try to do the best thing, always try to write honest reviews, and always try to be modest about his or her own results, when in reality that's just not the case. There's also this problem that we have incentive structures in science. If you want to become a professor somewhere, you have to have high-class publications, and there's certainly an amount of pressure that will force you to produce results, even if they aren't as well thought out as they could be. And those incentive structures are even worse if you go to industry. I mean, if you are in an industrial environment, the incentive structure is money. You're not doing what's best, you're doing what's most economic. And to believe that a complex system like a software system and its development can or should just be reduced to a one-dimensional number, which is dollars or euros or whatever currency you have, that's obviously unsound. And we are just broken in that regard. And I would very welcome in future renditions of this workshop to have someone looking into this and to actually find examples and to study this further, how it affects us and how it makes our lives worse. Maybe we can also address this a bit in the discussion panel, like what your ideas are on this. And then, of course, having said all that, there's also the necessary reality check. I mean, does it even matter if our verification systems are sound or consistent or nice enough? Because I can tell you that what happens in industry is something like we see here in the Castle Bravo bomb explosion. That was a big mistake and almost vaporized an entire island area. In real industrial environments, you have things happening like nuclear safety simulations, which are done in hack together C++ and are on budget constraints. I personally do have to do these. I've experienced companies hiring other companies to reverse engineer the inner workings of the software that the company has built. And like statements like, no one knows what our engineers did in 2018. And I've also encountered statements like, oh, a project where we just see 11 compile errors, that's normal. And of course, then you can ask, why are we sitting here? I mean, if that's the state of the world, isn't all hope lost? And should we really worry about having formally verified systems when even the basics aren't covered yet? But I actually do care about this. And I care for multiple reasons. One of them is if we want to have more attractive formal methods, we kind of have to guarantee that they actually work and provide some value and are not just some unsound, ill-defined figment of our imagination in which people will sink their money and then get a result 5 years later that everything ends in a catastrophe. I also think that it's a matter of intellectual honesty. So we as scientists have the task to be honest when we make mistakes, and we have to make progress by actually trying to find mistakes in existing science, which is something I believe computer science is not that good at. I know a few instances, but we rarely try and invalidate existing results. And the more empirical things get, the less we try it. And we have actually some mechanisms, like, for example, bug trackers are a great mechanism for this. But those are just not enough. For example, in our literature, once it has passed peer review, well, proper mechanisms for retraction, hard to find. And also, it's not something that is like celebrated. Or when was the last time you've seen a conference award given to someone who has honestly said, I made a mistake and this paper needs to be retracted? That's not something that is considered a good thing. But actually, it would be a good thing, I believe. It would actually be great if people who manage to get past peer review then say, wait a second, I found an error in my work and we have to investigate why this got past peer review. And just them getting beyond peer review is a sign that they are not just stupid and did something stupidly wrong that was obvious, but it must have been something more fundamental. And then, beyond intellectual honesty, I think that at some point, with the way our systems get more and more complex and complicated, we are bound for disaster at some point. We already almost skipped disasters, having avoided nuclear wars, where systems that monitored missile attacks were just giving wrong information. And something like this could happen any day. And it would be a catastrophe, depending on what it is. And we should try our best to avoid that. And finally, I personally, knowing what I know about how broken everything or most things are, I find this is a reason and some perspective to go on in computer science. If I wouldn't believe that we were having some possibility to make our systems better and to improve them, I think I should give up on it from what I know now. And I sort of refuse to just throw my hands in the air and give up and assume, oh, it's impossible and we can't do anything about this and we can't make our systems better. Yeah, and with that, I'd like to end this talk, and I'd like to invite you to stay a bit for the Unsound workshop and see some of the examples that have been found out where systems actually were unsound, and some of the things that we try and do to improve the situation. Yeah. Okay, that's it from my side. Are there any questions? I don't know if I have to do something to enable. No, I can hear you. Okay.
It doesn't look like we have any questions. You want to raise it?
I do.
Just one very small question. That in one of the early slides, you talked about the C memory model in the paper by Ernie Cohen and co being unsound. Was that result published somewhere? Or was that some of the folklore that people in this area just know about? Or
yeah, so there's I just did a quick search for that, trying to find. Let me go back to that slide. Yeah. So there was this paper cited down here by Cohen, Moskal, Tobis, and Schulte. And they describe how a memory model for C actually should look like. And in their first paragraph, they say there's a soundness issue if you're just using reference semantics for C. And you can probably go into that paper and find some of
okay. The unsoundness you're talking about there was in some earlier model, not in the model they were presenting in their paper.
No. What they did, as far as I can tell, is valid.
You meant that was actually the unsoundness was a flaw in their work, which I.
No. It's not a flaw of their work. I'm sorry if that caused the impression. No.
very much. Unless there's a final note, Marco, I think it's time to wrap up.
I think we can go to the coffee break. Yeah, I think we are 1 minute late now.
Cool. Thank you.
See you after the coffee break.
Okay, see you.